In this video, I want to demonstrate how to compute the expected value for a game of roulette. And I like the game of roulette for this kind of example because it's a simple game of just two outcomes, win or lose. And there's some interesting variations in how you can bet in roulette. Let's take a look at the example. So in this game of roulette, a player places a $6 bet on a single number, and the player has a 1/38 probability of winning. If the ball lands on the player's number, the player gets to keep the $6 and is awarded an additional $210. So the $6 is the wager, and the $210 would be the player's winnings if the player's number comes up. Otherwise, if the ball lands on a number other than the player's number, the player's awarded nothing, and the casino keeps the player's wager. So the two questions we want to answer is, what is the expected value of the game to the player? And if you play the game 1,000 times, how much would you expect to lose? So how I compute expected value in examples like this is to set up a table. The first column of my table would be just to identify what the outcomes are. And there are two outcomes. The player could win or the player could lose. Now each outcome has a value to the player. The value of winning to the player is the $210 in this particular situation, and the value of losing is a loss of $6. So you want to denote that with a negative sign. The third column will be the probabilities associated with each outcome. The probability of winning is 1/38, and the probability of losing is 37/38. Now my fourth column is the product x times p of x. So what I'm going to do is multiply across each row. So 210 times 1/38 gives me a value of 5.526321, and no, pardon me, 32632. Okay, I'm going out to 5 decimal places on this, and then for the second row, -6 times 37/38 gives me a value of -5.84211. Now what I'm going to do with that fourth column is to add those values. And when I add those two values, you can see one's positive, one's negative. What I'm going to get is -31579. Okay, now keep in mind our values in the column for X were in dollars, so the units on this quantity are also in dollars. The expected value of the game to the player would then be, if I round it to the nearest cent, -32 cents. Or if you had to enter it as a dollar value, you would put it in as -0.32, depending on how the question was asking you to format your answer. Okay. It's negative, of course, because casino games, the house always has an advantage, right? And there's the advantage that you see. And they choose their payouts by doing a similar computation, looking at the probability of winning, so that the casino always has that slight advantage. Now let's take a look at the second question. What happens if you play the game 1,000 times? How much would you expect to lose? So what I'm going to do is take my expected value out to 5 decimal places, and I'm going to multiply that by 1,000. When I do that, what I'm going to get is a -$315.79. And what that means is if you walk into the casino and you play 1,000 times, on average, a player who does that is going to walk out about $316 poorer than when they started. Again, there's that casino advantage. The only other thing I'll point out is as you're setting up your table, your probabilities, this column, those values should always add up to 1. Okay. Watch for the negative sign in the loss situation, and that should do it. Some of the variations you might see would be the different kinds of bets. This is a single number bet example. If, for example, you had a 2-number bet, the probability for betting on two numbers would be 2 over 38, and then the payout would be slightly less to compensate for the increased risk or increased probability of winning. Likewise, a 4-number square, when you put the chip in the middle of a square of 4 numbers, your probability of winning would be, let's say, 4 over 38, and then the payout in that case would again be commensurately lower in that situation. So those are some of the variations you might see for this kind of problem, but all you have to do is set up the table in the same way that I just showed you and go through the same steps. Whenever possible, when you're computing the x over p of x values, is to either do this computation in one step so you can minimize round-off error, or carry your values out to 5 or 6 decimal places before you add them. Okay, thanks for watching.